Hi, and welcome to another video of the A-Level Maths Explained series. My name is Diego, a research student in algebra at the School of Mathematical Sciences at Queen Mary, University of London. And today we will be talking about exponentials and logarithms. The whole world has been in shock since early 2020, when the COVID-19 was first identified by Chinese health authorities and started spreading to every corner of the planet. Our daily lives have been deeply affected by it in many ways. But what would you say if I tell you we have been watching on a regular basis the use of exponentials and logarithms since the COVID-19 pandemic started and even before, perhaps without even noticing? Both graphics show the number of COVID-19 infected individuals in the United Kingdom. In the x-axis, we find a progression of dates from 15th of February 2020 until 22nd of April 2021. And in the y-axis, we find numbers equally spaced representing population. Both graphics, despite looking rather different, represent the same dataset. In one of them, representing linear scale, the quantities in the y-axis follow an arithmetic progression, in which each bar is computed from the bar below plus 1 million. In the other one, logarithmic scale, the quantities in the y-axis follow a geometric progression, in which each bar is 100 times the bar below. Why does it make sense using a logarithmic scale instead of a linear scale when we talk about infection spread? It is because the health authorities want to show a flatter curve than they actually want to mitigate the increase of fear among the population? Actually not. It is because the expansion of the virus, and in fact of any virus, follows an exponential pattern. That is, if one person is infected, and it is known that the ratio of infection for a virus is 2, for example, it means that in average, that person will transmit the infection to 2 other people, so that in a certain time frame, we will have 2 infected people where there was only 1 before, assuming the original person either overcame the infection or passed away. Similarly, those 2 will infect 2 others, and so we will have 4 infected, and so on. Still, why are logarithmic scales relevant to representing infection data? Let us recall what are the logarithms and where they came from. An exponent is the number of times a certain number that we call basis is multiplied by itself. For example, in 8, which equals 2 to the power of 3, we have that the exponent is 3 and that the basis is 2. Therefore, we say that the growth of a quantity is exponential when the quantity is multiplied by itself a certain number of times, and it implies a sharp increase in that quantity. Logarithms appear for the first time in the work of the Scottish mathematician John Napier, 8th Laird of Merchiston, in 1614, and soon became very popular among big merchants and accountants for its utility as a tool to simplify big operations, as we will see in a moment. Consider a geometric sequence, that is, an infinite set of numbers in which each term is k times the previous one. For example, 1, 2, 4, 8, 16, 32, etc. is a geometric sequence in which each term is 2 times the previous one. Likewise, 1, 10, 100, 1000, etc. is a geometric sequence in which each term is 10 times the previous one. Now, let's write this as 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and so on, and respectively 10 to the power of 0, 10 to the power of 1, 10 to the power of 2, etc. We can see that the nth term is going to be a multiplied by k n minus 1 times. That is a times k to the power of n minus 1. Mathematicians call this correlation logarithm, which comes from the Greek logos, which is proportion, and arithmos, that translates to number. And as you might have already known or remember, we define the logarithm as a function depending on a number, the basis. Let a, b, and c be natural numbers. Then we define the logarithm in base a of c as b if and only if a to the power of b equals c. So the logarithm of a number is the position in the geometric sequence defined by the basis, or equivalently, the exponent one needs to raise the basis to obtain such number. Using our examples of sequences, we have that the logarithm in base 2 of 1 will be 0. And for example, the logarithm in base 10 of 1000 will be 3. Two things we should note here is that the logarithms in base e, which is the irrational number whose first tens are 2,71828, are called Neperian logarithms to honor their creator, John Napier, and also that we can observe from the formula that the logarithm is the inverse function of the exponentiation. But why did we say they became popular due to their usefulness to compute operations with large numbers? Back in the 17th century, calculators had not been yet created, other than the abacus, and therefore all computation had to be made by hand. Imagine how awful the job of an accountant had to be at the time. Since we know that given true numbers expressed as powers of the same number, x equal a to the power of b and y equal a to the power of c, their product is the power of that number and the addition of the exponents, so a to the power of b times a to the power of c equals a to the power of b plus c, we have that the logarithm of in base a of x times y equals the logarithm in base a of a to the power of b times a to the power of c, which equals b plus c. But that is also the logarithm in base a of a to the power of b plus the logarithm of a to the power of c, which is the logarithm in base a of x plus the logarithm in base a of y. So what has happened here? We have transformed a multiplication of two potentially big numbers, x and y, into the addition of two much smaller ones, b plus c. Similarly, and given that a to the power of b minus c is a to the power of b times a to the power of minus c, which is a to the power of b over a to the power of c, we have for free that the logarithms also transform divisions into subtraction. And it is clear to all of us that adding and subtracting are far simpler operations than multiplying and dividing when we have to do them by hand. But let's go back to our graphic on COVID infections in the UK. Since the pattern followed by the infections of a virus is a geometric sequence with a certain ratio k, we have that if there is one infected in a given time, there will be k infected, then k squared infected, and so on. Therefore, the logarithmic scale gives a much more clear pictorial representation on what is the real spread rhythm of the virus than the linear ones. If our logarithmic graphs would show a straight line, it would mean that none of the measures taken to prevent the spread of the virus could have had any impact. However, since our graphs show a clear flattening of the curve, it means that the various restrictions, together with the later vaccine rollout, have crashed dramatically the spread of the virus. This is why you could hear experts obsessing about the importance to decrease the rate of infection below 1, because if n is a number between 0 and 1, then n to the power of k is less than n for a natural number k. And if the rate of infection k is kept below 1, the virus will eventually extinguish and the pandemic disappear. If you would like to know where I am obtaining this data from, it's all taken from the website Worldometers. which provides up-to-date data on many topics such as health, food, pollution, and many others. I hope this short video worked as a reminder that even if a good part of the mathematics we learn in school and high school might seem useless to us at the time, they might be needed not only for those who decide to pursue a degree in science or social sciences, but also to interpret and analyze data correctly. And in particular, I hope that this video has been interesting to you and will motivate you to appreciate the relevance of exponentials and logarithms via one of its many applications. Thank you for watching.